Hi, good afternoon, and welcome to the second INPHOMIR webinar, Advancing Navigation and Sensing with Indium Phosphide Integrated Photonics. It's a pleasure to meeting you today, and many thanks for being with us. My name is Sara Tana. I'm the Dissemination Manager of INPHOMIR project, and I work at Next Innovation Hub, that is the company that supports the organization of this kind of webinars. Today we will have the speech of three different partners of the project. The first speech will be given by our project coordinator, Lorenzo Mancini. Lorenzo Mancini is a researcher at the Photonics Research and Applied Navigation Sciences Laboratory of GEM Elettronica, and his work focuses on the development of fiber-based and integrated photonic solutions for inertial and remote sensing. So you will know more about the project and about the activities that he's performing inside the project. Our second speaker is Javier Leitens, Associate Professor in the Department of Electrical Engineer at the Eindhoven University of Technology. His main research focuses on photonic IC design for applications in communication and sensing. And then our last speaker of today is Mikhail Belkin, that is a professor in the Department of Electrical Engineering at the Technical University of Munich. I would like to remind you that this webinar is registered, so you will find the registration of this event on our project website, infomir.eu, and we will share it also on our social networks. So I invite you all to follow us on LinkedIn if you haven't already done it, in order to be updated with all the news related to the project, and also to share the event to the people that you think can be interested to watch it again. So our first speaker is Dr. Lorenzo Mancini. So Lorenzo, I kindly ask you to share your presentation and start with this short introduction of the project.
Yes, thank you, Sarah, for the introduction. Thank you all for joining today. So I'm sharing my screen now. Can you see my screen?
Yes, we can see it. So the stage is yours.
Thank you so much. So yes, hello everyone. As Sarah as Sarah mentioned, I'm Lorenzo Mancini from GEM Elettronica, and I'm going to give you an introduction of the INPHOMIR project, and I was willing to start from a short introduction of GEM Elettronica, which is a company which is part of Leonardo company, and whose core business focuses on remote sensing, mainly radars, and inertial sensing, mainly fiber optical gyroscope. And so here you see a graphical representation of all the products. And in GEM Elettronica, we also have a R&D lab, which focuses on photonics for navigation. And so I'm part of this lab mentioned by Sarah. And in GEM, we have a certain number of know-how. Let's say we have a know-how which is of interest for INPHOMIR, basically related to integrated photonics, development of inertial sensing solutions, and infrared remote sensing. And we have a know-how related to photonic devices industrialization. So let me introduce the project. So the project INPHOMIR is a project which is funded by Horizon EU Horizon Fund, which is led by GEM Elettronica, and it is participated in by 8 partners. We have 4 academic, let's say R&D academic partners, and 2 end users, and also Warrant Next, which is managing the communication dissemination and exploitation. And so the main objective of INPHOMIR is developing monolithic photonic integrated circuit devices based on the indium phosphide platform for applications of interest in autonomous navigation for aerospace drones and low Earth orbit nanosatellite space navigation. And I will show you in a minute. We are targeting mainly two kinds of devices, which are integrated gyroscopes and LiDARs. So let's start from why we decided to work with the indium phosphide, let's say indium phosphide photonics. So the project INPHOMIR is based on this technological platform. And the indium phosphide platform has been used for decades for developing the in optoelectronics for laser modulators. And in more, let's say, recent years, the technology for growing this kind of material improved. And now also it is possible to have also passive components of integrated circuits of good quality. So we can have also passive, for example, waveguides with low losses. And so this allows to have monolithic integrated circuits where we build both the active and passive components on the same platform. Also, indium phosphide is of interest because it allows for operating photonic devices in a wide range of wavelengths, going from the short infrared to the long infrared, which I will show you later. It may be interesting for some kind of applications, such as range finding or LiDARs. And the third interesting point of this indium phosphide platform is that nowadays it's scale up because there are nowadays 4 inches pilot lines which offer multi-project wafer runs with well-developed PDKs, and so yes, it's almost ready for industrialization, let's say. And so, as I said, in INPHOMIR we target 2 kind of devices. And in terms of inertial sensing, the project plans to work on the near-infrared platform proposed by TUE, develop the all passive and active building blocks needed for inertial sense. So let's say an inertial sensor, develop advanced resonators on the same platform, and with these building blocks, we aim to develop and fabricate a resonant integrated optical gyroscope. Analogous in the same way for the remote sensing part of the project, we rely on the mid-infrared platform proposed by TUM. Again, we develop all passive and active building blocks. Then we target advanced mid-infrared MIR functions such as balanced heterodyne detectors, and with all these building blocks, we plan to develop a frequency modulated continuous wavelength LiDAR. And finally, the idea is finally to take these sensors and work with both these sensors within a sensor fusion approach for navigation applications. Okay, so in terms of quick overview in terms of positioning, so all these these technologies involved in INPHOMIR starts from a TRL which is around 2 or 3. Here you have some examples of the building blocks and of the building blocks of interest and the final gyroscope and near LiDAR. And the idea is to bring these technologies to a TRL of 5. This is done within the project. The plan is to go from lab testing to use case validations with our end user partners, and also to propose an industrialization roadmap for the 2 technologies. Okay, so in terms of inertial sensing, so I prepared a short slide just for introducing a resonant optical gyroscope, let's say. So as all optical gyroscopes, it's a device that measures angular velocity, the angular velocity of an absolute rotation. It is based on a relativistic effect, which is the Sagnac effect. But the main difference with respect to, for example, the fiber optic gyroscopes or laser gyros, the way in which it works is a little bit different. As you can see my mouse, we have a laser source, then we have two paths for the light, one let's say clockwise and counterclockwise of light passing through a high quality resonator. And then the light coming out of the resonator, at least in this configuration, is detected by these two photodiodes. And the idea is that in this kind of configuration, typically what is done is that the laser frequency is locked to one of the resonant frequencies of the resonator by some sort of feedback loop control. And then from the other arm, so we look at the other, for example, in this case, the counterclockwise rotation, and we see the difference in terms of positioning of the frequency of light with respect to the center of the resonance. And from this information, we can extract the information on the angular velocity. And the advantage of these kind of structures is that it's principally it is ideal for integration because these resonators can be really small, and all these components can be in principle integrated in one photonic integrated circuit. So in terms of state of the art, INPHOMIR proposed a monolithic PIC, so everything is integrated on the same integrated circuit. And so the idea is to compare this kind of object with MEMS gyros, which are also integrated, but they are less performant than other technologies such as FOX. But they are obviously smaller. So the idea is to develop something which is small and more performant than a MEMS gyro. And so now let me show you where we are with the project right now in terms of inertial sensing. So the project now is essentially in the second half of the timeline of the project. So we already worked on the design and simulation of the all various building blocks. We developed the basic building blocks such as the low loss waveguides, lasers. We are working on integrating all the active components on the same chip. And we are developing the high quality resonators and the monolithic PIC, where we will integrate all the active building blocks on the same circuit. And in parallel, we are working on the electronics and the readout. Okay, so in terms of remote sensing, instead, INPHOMIR plans to develop, as I said, a frequency modulated continuous wavelength LiDAR. And so just let me show you a quick sketch of how this works. The idea is that instead of working as a more common time of flight LiDAR, which send a pulse and then looks at the delay, the received pulse, it works with coherent detection of the two waves. And the advantage of this is that for let's say, somehow simpler electronics, it allows to have information on the position and on the speed of the target. And this kind of device can have its interest for applications in navigation, such as a simple obstacle avoidance, or for example, can be used for navigation with respect to a reference or simultaneous localization and mapping. Again, in terms of state of the art, the idea is that there are plenty of companies fabricating LiDARs, let's say, but the idea is that there are no developed LiDARs which are fully integrated, and they work in the mid-infrared spectrum. The interest of working at higher wavelengths, such as 4 and 9 microns, it's due to the lower optical attenuation of the atmosphere. as you can see here. And in terms of performances, INPHOMIR tries to target something which is again fully integrated on one PIC, and it allows for a few hundred meters of ranging and reasonable speed resolution. Okay, so in terms of advancements, in INPHOMIR, the first part of the project, all building blocks were simulated and developed. We started fabricating the low losses waveguides, the QCL and QCDs, the sources and the detectors, and the passive components. And we are working on the advanced functions such as narrow line with QCLs and balanced heterodyne detectors, which will be integrated in a final frequency modulated continuous wavelet lidars, and we are now currently working on these integrated PIC devices. I will just quickly mention that there are also activities related to packaging with one of our partners, and so the idea is that these PICs will have to be also packaged for being tested by the end users, and these packaging activities are done both for the NIR and MIR platforms. Okay, and then the last part of the project takes care of the sensor fusion implementation. So obviously it takes into account both the electronics and all the software development for filtering the signal and the two sensors working together, such as applications of Kalman filters, which are normally used in navigation application, and the use case validation, which consists in testing the devices for autonomous navigation applications. So the idea is to try to integrate these devices on a drone for test flights, and the same thing for the low Earth orbit nanosatellite navigation. The idea is to try to integrate the devices in CubeSats and just test the algorithm for navigation. So for concluding, the idea is that in INPHOMIR, I already introduced the objectives. In terms of status of the project, we defined the architectures and we developed all the basic building blocks. Now we are working on the implementation of these building blocks on the final PIC devices, both for the gyroscopes and for the LiDAR. And in the second part of the project, we will test these devices and test them with respect to the use cases for validating their operation, the use cases. And that's all from my side, I think.
Many thanks, Lorenzo. If anyone has any question, please feel free to write in the chat, and I will be pleased to read them and to ask to Lorenzo. At the moment, we don't have any question. So maybe we can go on, and then after, if someone has any question, I will read you, Lorenzo, in order to answer. Okay, so we can go on with the second presentation. The second speaker of today is Xavier Leitens from the Eindhoven University of Technology, and the presentation is entitled Optical Gyroscope in Monolithic Indium Phosphide. So many thanks for being here and welcome.
Thank you. Let me share my window.
Yeah, feel free to share your presentation. Okay, if you can put it in presentation mode, please.
Yeah. Okay.
Perfect. Yes, we can see it. So the stage is yours.
Good. Thank you. And thank you all for being here. Welcome this afternoon. My name is Xavier Leitens. I'm Associate Professor in the Photonic Integration Group at the Eindhoven University of Technology. And together with my colleagues, Rajiv Shenoy and Ashish Prasad, we participate in the INPHOMIR project. And I will give you a status update of what we are doing. So let me start by just going to the very basics. And this optical gyroscope is based on the Sagnac interferometer. So here's a schematic of the Sagnac interferometer. Let me get it. Where light enters, and there's a semi-transparent mirror, and part of the light goes in the counterclockwise direction, while the other part goes in the clockwise direction. Now, if the whole gyroscope is rotating while measuring, then by the time the clockwise signal reaches the mirror will have moved a little bit further and the path length becomes longer, while the counterclockwise signal sees a shorter path. And this creates a phase difference, and this phase difference can be measured and is a measure for the rotation of the gyroscope, of the interferometer. Now, this can also be done for example, with an optical fiber. So if you have an optical fiber spool, then you can also see the phase difference between the counterclockwise and the clockwise directions when this is moving. And this is what we use in the project. It can also be an integrated waveguide, for example, instead of a fiber. So you need, in addition to the resonator that I just showed, you need a laser for generating the light. You need modulators for enhancing the sensitivity, and you need the detectors. Now, all of this we would like to integrate on a single monolithic indium phosphide chip. So that would include the laser, the modulators, the detectors, but also the optical resonator. Well, that's not an easy task, and I'll show you how we do that. And within the project, this is done in collaboration with isn't it? In collaboration with GEM Politecnico di Bari and Tyndall for packaging. Okay, let me get to the contents of my talk. I will show you how we do the active-passive regrowth. That will create the amplifier, a modulator, and a detector on the same chip. Then what we do to reduce the waveguide losses, I'll come back to that in detail. And then the development of several building blocks that we use to build this full circuit. And then I'll come with some conclusions. Okay, first to the building blocks. Well, what we need for the integrated gyroscope is the resonator that's shown here. Because the path length or the more sensitive gyroscope requires a long path length, we need low loss waveguides, and the waveguides that we have in our standard technology is not low loss. Furthermore, we need splitters to couple into this into the resonator, and 50-50 splitting that is available is not optimal, so we also need new splitters. Well, amplifiers, lasers, and detectors for the light generation, amplification, and detection, they exist, but the ones that we have at the moment are not so suitable. I'll come back to that. Modulators we also need, and waveguide crossings. For example, what you see here is a number of waveguide crossings that are also non-standard. I'll go through these things in a bit more detail, but first let me show you how we do the integration of active and passive components. And for this, we grow our layer stack in the clean room at TUE. For this, we have an Extron MOVP reactor, and this reactor can grow 12 4-inch wafers at the same time. We have etching for the different materials, different etching machines, wet chemical etching as well, and we have an ASML deep UV scanner for the photolithography, mainly of the waveguides. So how does this work? Well, these indium phosphide substrate, you can just buy them. So we buy the 4-inch indium phosphide substrate. This is a schematic of the cross section of such a wafer. They are put into the MOVP reactor, and then we first grow an n-doped indium phosphide layer, and then we grow in high index material. We grow multi-quantum wells. So the red part here is multi-quantum wells. We grow the p-doped indium phosphide because we need a PIN diode to drive the laser. And then we stop, and then we mask parts here which are to become the amplifier and the detector. These share the same cross-section. Then we etch away the active part in most of the wafer and keep only active parts where we need the amplifiers and detectors. And then we regrow. With a passive material, so transparent material, indium gallium arsenide phosphide. We regrow the core of the waveguide, which is the guiding layer. We regrow undoped indium phosphide, and we remove the mask and then grow a common cladding layer on top of it. And then finally, there's the contact layer as well. So with this, we have the diode structure ready. We can do a waveguide. So for making these, we first remove the contact layer where we don't have active components, and then we etch structures, waveguides for the amplifier, the phase modulator, and the waveguide. So we etch the waveguides, and now what we have is a structure that provides amplification, a structure which reversely biased, well, after we put the metal, which reversely biased can provide an electro-optic phase change, electrorefraction, and we have a waveguide for guiding the light. So this is then a 3D view of how this looks like. The white part here is where the light sits, and the three waveguides types that you see here are very similar, and that's not a coincidence because they are made in more or less the same process. Well, if we look in a bit more detail at the passive waveguide here, this is a cross-section with a mode solver. You can see that this mode overlaps a little bit with the p-doping on top of it. And that's what is the main problem that we have for the loss, because if you look at the breakdown of the losses, you see that the scattering from the roughness of the sidewall of the waveguide is 0.3 dB per centimeter. The N-doping doesn't influence the light so much, is 0.2 dB per centimeter, but the P-doping is 2.5 dB per centimeter. So indeed, if you remove the doping and you measure passive waveguides, you get a loss which is 0.5 dB per centimeter or less. But yeah, we do need the doping for the amplifier and the phase modulator and the detector. So, well, what we try to do is to make a local doping only there where we need it and have the waveguides without doping. So this is the standard way of making the structures with p-doping already in the growth. Now what we do is we grow the same layer stack, essentially the same layer stack, but now without the p-doping. And then we have the wafer, and on top of the wafer we put a mask, and the holes in the mask, they are there where we have the amplifier, and also the where we will have the phase modulator. Then this is put in back in the reactor again, and with this reactor we will drive zinc through the openings in the mask only at those locations where it's needed. So the amplifier, the phase modulator need a PIN junction, and so they that's where we drive the zinc through this mask. So the zinc will be going in there, and that will provide the p-doped contacts for the modulators and the amplifier. Then we remove the mask again, and we etch the waveguides as we did before. And now we have the similar structure, but now with doping only in the parts where we need it, and the waveguide is low loss without doping. This requires to control the depth of the p-doping, which is well, depending on the machine settings, but it's a process that is proportional to the square root of the time which you use to do this. Here's some experiments that we did on the layer stack that we have here. So you can see it's not only dependent on the time, but it's also dependent on the pressure and on the temperature, for example. And here are different experiments that we did to drive the zinc into the indium phosphide, and we should stop at the right point. This is a little bit too deep, so we are still calibrating, but that is well, we are convinced that we can get to the right depth here with the results we have. So, well, that ends the first part where I show how we do the active-passive integration and how we do the local p-doping. And then the rest of my talk is on some of the building blocks. So let's start with the spiral resonators. There's, well, two ways to do it. One is to use the low loss waveguides and make the resonators. And we have several experiments in which we made those passive low loss resonators. And then the second way we are doing is having the resonator, but then have tiny amplifiers in each of the turns of the resonator that will compensate for the residual loss in the waveguides. So we hope with this, because we have active passive integration anyway, we can also use it to amplify and to compensate for the losses. Then we need to control the coupling to the resonator, and for this we can use directional couplers. These were also not available, so had to be developed. Essentially, it's two waveguides that are brought in close proximity, and then light will couple from one to the other. The simulated coupling is shown in the dashed line. The measured coupling is shown in the dots, and you can see that there's a huge difference between them, much larger than we anticipated, partly due to the fact that the edge depth between the waveguides is not going to be as deep as was simulated. We think that with the data that we've gathered, we can still design for the next run. We can still design couplers with more or less the coupling that we need. Another way of doing the coupling is with the multimode interference coupler that is shown here. The 50-50 coupling is there would be a too large fraction coupled out of the resonator, so we want a resonator. We want a coupler which has a larger bar port splitting ratio, and the regular one, which gives, for example, 72-28% splitting, actually has the large fraction in the cross port, and in order to make it in the bar port, we had to make a new design that is 3 times as long as the previous one. And here's a simulation showing that there's not much wavelength dependence, and also the tolerance towards the width difference is quite acceptable. Then for the crossings, if we have the resonator here, we need to cross to get out of the resonator. We can use different types of crossings. One is just to cross two waveguides, just make a waveguide crossing like this. Or we can taper up to a wider waveguide and have the crossing in a wider waveguide. There's two effects that play a role here. One is if your waveguide is narrow, your diffraction will be large, but the part where the light diffracts is short. Here your waveguide is wider, the diffraction is less, but the path to over which it diffracts is longer. It turns out that the wider device has a lower loss, so that's a preferred one. That's one way in which to do it. The second way in which to do it is to use an MMI, and that's shown here. So we enter the light in one input. It starts to interfere, and the interference pattern is such that at some point we get an image of the input waveguide here. And if at that point we have a crossing, then this light here doesn't see the crossing waveguide, and we can make very low loss crossings. The problem is that if we need, say, 10 or more of those crossings, that the whole structure becomes very sensitive to width variation. So that's shown in the picture here, where the nominal width is shown here in the dashed line and is very low loss for 10 crossings. But then if you even change by 50 nanometers, for example, you get a much higher loss. And then in the end, if we have 10 crossings, it's preferred to have the waveguide crossing with just a wide waveguide. So in the final design, what we did is we used the wide waveguide for this crossing, and in each of the perpendicular crossings we use this MMI, and then it's just one crossing. Yeah, then the last component that we have is a low line width laser. The whole system needs to be driven with the low line width laser. This is one of the low line width lasers that was developed in our group, and doesn't require any additional components. So it's built from phase shifters, standard multimode interference couplers, and the SOA, the optical amplifier, that are available. So this is something we can also do in the new platform. This is the schematic of the tunable laser. This is a picture of a fabricated tunable laser. Here are measurements. It has a low line width, certainly low enough for the project needs. This particular device is also packaged in an experimental package by Tyndall. This small thing here is the chip that actually contains 4 of those lasers. One of them is connected to a fiber, and then we can use it in the experimental in the experiments. So the last design that I show here actually combines a number of the building blocks that we need in the final system, and it's done in such a way that we can separately test those building blocks. So it has multi-building blocks on a chip. It's going to be packaged with an array by Tyndall as well, and we are currently testing the fabricated devices. Here's a picture of the measurement setup, just seeing if they are functionally okay, and then they will be packaged and they are tested by GEM and Polytechnico to replace the current bulk components in the setup that they are using now. Then eventually what we have to do, and what we are doing now for the final stage of the project, is to design the full integrated gyroscope with different architectures. We have a full wafer to design for, so that's that should be feasible to try out multiple architectures. Then we have to fabricate them, and after initial testing, and if they are the initial testing is okay, they will be packaged and then go for system testing. So with that, I would like to conclude. So we have the active-passive regrowth process available, as well established, the zinc diffusion, and there's now the final calibration. So we have the starting point. We just need to fine-tune the zinc diffusion. All the relative building blocks that all the relevant building blocks that we need have been developed and tested. Several architectures for the final integrated gyroscope are being designed. And with that, I would like to thank you for your attention.
Many thanks for your very interesting presentation. I remember all that if you have any question, please feel free to ask them and write them in the chat or in the chat for the question DNR. And thank you very much. We are looking forward to receiving any question for you. But in the meantime, I think that we can go on, because at the moment we have no question. So we go with the last presentation of today. Last presentation of today is about mid-infrared photonic integration and nonlinear optics on indium phosphide, and Professor Michael Belkin from Technical University of Munich will give this last presentation. Many thanks for being here. We cannot hear you. Please, if you can switch on your microphone.
Yes.
Thank
Can
you very much.
Hear me now?
Yeah, we can hear you very well.
Perfect.
And we can see also the presentation.
Very well. Thank you, Sarah, for the introduction, and thank you everybody for attending this webinar. I will talk about our effort on mid-infrared photonic integration on Indium P. For the sake of time, I'll skip the part about nonlinear optics actually, but I have some backup slides in case somebody is interested specifically on the nonlinear optics part. My talk is going to be a little more general. It will not focus just on the INPHOMIR project, but it will talk about mid-infrared photonic integration in general. And at the end of the talk, I'll give you some examples from the INPHOMIR project. Unlike near-infrared photonic integration, mid-infrared photonic integration is at its infancy. And the photonic integrated circuits that I'm going to show in this talk are actually the first photonic integrated circuits where distinct active components were integrated on the same indium P chip in mid-infrared spectral range. So I'll start with a general introduction for the motivation of mid-infrared photonic integration. Similar to near-infrared spectral range, mid-infrared spectral range has a lot of its own applications, starting from spectroscopy and sensing to because it's an important spectral range for spectroscopy and sensing, because vibrational absorption fingerprint of molecules is exactly in the mid-infrared spectral range, wavelengths from 3 microns down to 15 microns. Mid-infrared and long-wave infrared spectral ranges, mid-infrared is from 3 to 5 micron wavelengths, and long-wave infrared is from 8 to 15 micron wavelengths, are regions of atmospheric transparency. You can see the atmospheric transmission spectrum. And unlike near-infrared and visible, radiation at this wavelengths is less susceptible to adverse weather conditions, such as, for example, fog, sandstorms, or rain. It's known that you can penetrate much deeper in this adverse weather conditions at these 2 wavelengths windows because of reduced scattering. And then there are a lot of other applications for this spectral range, which would also benefit from photonic integration. Now, the type of lasers that operate in the mid-infrared spectral range are different from the type of lasers, semiconductor lasers, that operate in the near-infrared spectral range. Unlike diode lasers that are based to conduction to valence band transitions, in the mid-infrared spectral range, we have quantum cascade lasers that are based on inter-subband transitions, transitions between electron subbands in a conduction band of a semiconductor superlattice or heterostructure. This technology allows one to use the well-established indium P-based materials developed for telecom lasers to build devices that generate and detect light at mid-infrared frequencies. In fact, you could use the same material system to design devices operating from let's say 3 microns all the way to longer than 15 microns. And these devices operate continuous by room temperature. Another technology that may be used to build semiconductor lasers in the mid-infrared spectral range is interband cascade laser technology. These lasers are grown on gallium antimonide substrates and use indium arsenide, aluminum antimonide, gallium antimonide based superlattice to create this kind of structures. They provide actually very nice performance in the 3 to 6 or 7 micron, and then they stop operating at room temperature beyond 7 micron wavelengths, at least at this moment. They have low threshold power density, but their integration on gallium antimonide substrate would be difficult for a number of reasons, and one of them is lack of available foundries to do that, and very high cost of the materials and substrates. Detectors in the mid-infrared spectral range, we have traditional mid-infrared detectors based on, for example, mercury cadmium telluride, indium arsenide, indium antimonide, basically low band gap semiconductor materials. But you could also use thermal detectors or so-called quantum well-infrared photodetectors. Quantum well-infrared photodetectors could also be implemented on the indium P platform, and you could also use so-called quantum cascade detectors. These quantum well-infrared photodetectors and quantum cascade detectors, they also use inter-subband transitions, that is, transitions within the conduction band of a semiconductor superlattice to create states for light absorption and for the transport, and therefore they can be designed for operating at any wavelengths in the mid-infrared spectral range using essentially the same materials platform. In our case, it's indium P platform. You could also, at certain wavelengths, design devices that at bias would operate as lasers, and at zero bias, they would operate as detectors using inter-subband transitions. So now we perform our integration, mid-infrared integration on Indium P. And at this moment, since the whole topic of mid-infrared photonic integration is at its infancy, we may want to think about the advantages and disadvantages of Indium P as a platform compared to other available platforms for mid-IR photonic integration. And the biggest competitor, just like the telecom spectral range, is silicon photonic integration. However, unlike telecom spectral range, here we have some clear advantages over silicon. The most important one is that silicon is not really transparent beyond the wavelengths of about 7 microns. This is the absorption of float zone, high resistivity silicon, and because of different vibrational modes, it basically starts having significant absorption, 5 dB per centimeter in the bulk material, starting from about 7 microns. You could switch silicon to germanium, and there are some germanium-based mid-infrared photonic integration waveguides that circumvent this problem to a certain extent. But on the other hand side, Indium P platform in the mid-infrared spectral range, and that includes Indium P, Indium gallium arsenide, aluminum indium arsenide, and all these semiconductor materials, it is completely transparent, nominally speaking. If you forget about some background free carrier concentration and small replicas of the optical phonons that actually sit pretty far at 30, 40 micron wavelengths, 50 micron wavelengths in these materials. So if you assume only free carrier losses, then at doping density of, let's say, 5 × 10⁻⁴, your intrinsic material losses would be well below 0.5 dB per centimeter in the entire. Here it's plotted, 5 to 12, but actually you could extend it 3 to 15 micron range. We have sufficient index contrast for Indium P, Indium gallium arsenide, Indium P gallium arsenide antimonide, which is another compatible 3.5 material on Indium P. So you can build the waveguides. So you have all these potential benefits of using the Indium P platform, because similar to near IR, it allows seamless integration of lasers and detectors. Now, the lasers and detectors are going to be based on inter-7 transitions, but still grown on Indium P monolithically. It has good thermal properties, low optical losses, also high kernel linearity, an order of magnitude at least higher than that of silicon for potentially a nonlinear optical operation of these devices. Since near-IR photonic integration, mid-IR photonic integration at its infancy, the first step that we've done is to actually fabricate and characterize the losses in these devices. And as I mentioned, the intrinsic losses of these materials are expected to be very small, but the losses due to sidewall contamination and oxidation and other imperfections in processing may result in significant amount of loss. So we use this methane hydrogen-based etch, similar to what many near IR people are doing to etch this high-profile waveguides, based on in a core made of semi-insulated or lightly doped indium gallium arsenide and semi-insulated or very lightly doped Indium P cladding layers. And we then characterize them using this simple optical setup where we couple light in, couple light out, and observe Fabry-Pérot oscillations in the transmission. Since we can compute very accurately the facet reflectivity of a cleaved facet of our waveguides, from the depth of this oscillation, we can deduce the losses of the waveguide. And these are the typical parameters of our waveguide. The core is actually varied from 1.5 to 3 microns, depending on the wavelengths where we operate. We use either lightly doped or semi-insulating materials, and then we can deduce losses. The intrinsic losses, even with the slight doping, are very low. But the actual losses are significantly higher. And for very narrow waveguides, we read first 11 dB per centimeter. However, a significant amount of that loss is due to surface contamination of the waveguide sidewalls. And so we use this post-processing tricks similar to the tricks that are used by silicon photonic people, where we First of all, of course, we clean the surface from polymers that is deposited during etching using acids, and then we cyclically oxidize and then of the sidewalls and remove the oxide with the HCl acid. And that leads to quite dramatic improvement. So first, if we just apply acid to clean the sidewalls from polymers and everything else, we reduce the loss. And if we then use cyclic oxidation, deoxidation, the loss can be brought down to below 1 dB per centimeter. And this is for the 5 to 6 micron wavelength range. And then we also done testing for the 5 to 11 micron wavelength range. And again, this cleaning helps. And then if we use semi-insulating materials for bottom cladding, top cladding, and the core, the loss can be reduced even further. We've also demonstrated that we could fabricate critically coupled ring resonators in this material system. And this here we used iron doped wafer with iron doped core and cladding layers and a little thicker core. And these are some fabrication results. We use approximately 700 nanometer gap between the bus waveguide and the ring waveguide, and we demonstrate a 400,000 Q factor, which is better than the best results demonstrated in silicon photonics at this wavelength range, and these results are constantly improving. So I expect Q factors close to 1 million will be reached soon in this materials platform. We then explore the different integration concepts for different active regions. And when I say active region, this could be different lasers, quantum cascade laser at one wavelength, quantum cascade laser at another wavelength, or it could be some quantum cascade lasers and some detectors, or it could be some quantum cascade lasers and some modulators. The idea is that we could, similar to what is done in near-infrared, we could grow selectively active regions or different materials at different parts of the wafer and then connect them by passive waveguide. And we could use two types of configurations. One is that the bus waveguide that connects all these active parts is below these active parts, and then we need to taper these parts to couple light from them to the underlying waveguide, or we could remove some of the material and then selectively grow passive waveguides in between these parts and use that sections to connect these parts. The first demonstration is to grow two different active regions with the waveguide going below, and this is our recent demonstration. Here we grew two active regions for quantum cascade lasers, one operating at 6 microns, another operating at 7 microns, and then fabricate distributed feedback devices and then use this directional coupler to couple them together. Quantum cascade lasers are devices based on inter-subband transitions, and one of the advantages that inter-subband transitions have over traditional diode lasers is that devices based on inter-subband transitions are much less critical to the to the defects during the epitaxial growth. So when we do, for example, selective removal and overgrowth of the active region, they would have or expected to have much lower sensitivity to the defects. This is because inter-subband devices already have very short carrier lifetime determined mostly by optical phonon scattering. So an additional increase of the lifetimes due to some impurity scattering or dislocation scattering only play a minor role in their performance. This is unlike diode lasers where radiative lifetime is very sensitive to defects. So in any case, we've developed these directional couplers. This is how the edge structure looks like, and we've demonstrated that, for example, we can transmit, say, 5 micron radiation with nearly 100% and couple, let's say, 8 micron radiation also with nearly or close to 90% to the bus waveguide. And then similar directional coupler was then implemented to combine the light of two devices. When we grow the active regions, we since in our case, we use molecular beam epitaxy to grow these active regions, we could not use the silicon dioxide mask to prevent growth. And in our case, we have physical deposition in metal organic vapor phase epitaxy. We could have done it even more efficiently, but with MBE, we have to grow one active region, remove it, then grow another active region, and it will be deposited everywhere. Then we remove it from the top, and then use that edge top layer to stop, and then we basically have two different active regions on the wafer that can be then processed into devices. We've demonstrated that if you grow the same red and blue, the same active regions, then the laser performance does not change significantly. And you could see black and blue data that corresponds to this red and blue sections, one grown first, the other one is regrown. No significant changes in the performance, and wall plug efficiency is roughly the same. So we then grew different active regions with 6 and 5 microns and demonstrated this peak. This is how the wafer looks like. And this is the first demonstration actually of a functional photonic integrated circuits in the mid-infrared spectral range with two distinct active regions integrated on the same platform. So some device operation at room temperature, and you could see some emission spectra targeting SO2 and NO2 gases. Also, the far field profile, since they're coming from the same facet, is well overlapped, and basically this shows the capability of this mid-IR photonic integration on Indium P. For the INPHOMIR project, we followed a slightly different approach for photonic integration. This is because our photonic integrated circuits for the INPHOMIR projects are going to be more complex. And so here we actually, after growing active region 1 and active region 2, maybe active region 3 even if necessary, we selectively remove them, and then using metal organic vapor phase epitaxy similar to what Javier talked about in near IR, to fill the gap with the semi-insulating iron-doped indium gallium arsenide waveguide. And then we use the common upper cladding layer for the entire structure. We use very low doping for the cladding layer because free carrier concentration, high free carrier concentration would strongly affect the losses at mid-infrared frequencies. But at 5, 10 to the 15, we introduce no more than 1 dB per centimeter additional loss, actually significantly less than 1 dB per centimeter additional loss, even at 8 micron wavelengths in that passive waveguide. So this is how the active and passive look like. There is here the passive is made to be a little thicker, but by timing the MOVP growth, we could actually match their thicknesses pretty well. And now we build the first photonic integrated circuits for the INPHOMIR project. Here's the design for of a chip for a balanced heterodyne detector. It is based on 2 active regions. One is the active region for the quantum cascade laser, and a separately grown active region for the quantum cascade detectors. And then we have a 2x2 MIMO, where it is designed to have a 50% splitting of power for the 2 inputs. These are the header structures for the QCL and QCD designs. There is significant body of literature of how to design high-performance cascade lasers and detectors at different wavelengths. And so for the INPHOMIR project, we used some modifications of existing active region designs to tailor it for our applications. But this is a well-known 2-phonon resonance cascade laser design. For the detector, we used a configuration similar to that reported in the literature, and again adjusted it for our wavelengths a little bit. And for the 8-micron design, actually it is possible to design a quantum cascade active region that is simultaneously working well as a laser under bias and as a detector under zero bias, following this paper. So for the 8-micron peak, we actually don't even need to separately grow another active region on our wafer. The same active region could be used as a laser and a detector. For integration of the lasers, we need to integrate distributed feedback lasers, and we found that the best way to implement them in basically one single edge would be to use DV lasers with the sidewalk radiation. Since we operate at mid-infrared wavelengths, the period of the grating is longer than that of the DV grating for near-IR lasers, and it is and another advantage is that for inter-subband devices, you can actually etch your lasers through the active region, and all quantum cascade lasers, for example, are etched through the active region. This surface recombination plays no role in inter-subband devices, and that allows us to build this DV lasers in a single edge. And this is some of the performance of these DV lasers for operation at 3.3 microns, roughly, grown separately, and you could see that the performance is actually very high by QCL laser standards. And so recently we implemented this first photonic integrated circuits for the 5 microns based on the balanced heterodyne detection. So here's the image of a photonic integrated circuits. This is the laser section. Here we have passive waveguides, and also we have a passive waveguide here. And here's the 2 quantum cascade detectors. So there are 2 separate EPIs. One is for the laser, one is for the detector, and then there is actually a third epitaxial growth for the passive waveguide, and then they all share a common cladding. This is how the little chip looks like. In fact, it has 1, 2, 3, 4, 5, 6, maybe even 7 of these individual PICs, and we are testing them all together on the die. You have lasers, passive input also on that side, and detectors. Now the performance, we have CW operation at room temperature for the lasers with single mode emission at around 5 microns. This is the local oscillator for the double heterodyne detection. And then we have a 50-50 beam splitter that leads to the 2 detectors, and we could verify that the laser emission is indeed split 50-50, roughly. This is the readout of the detectors as a function of pump current of the laser, slightly different device, so therefore current density is a bit lower, threshold current density is a bit lower, but nevertheless you can see 50-50, close to 50-50 splitting. And then we could also couple lights through the passive waveguide and also observe the detector signal in detector 1 and detector 2. Here we are not too close to 50-50, probably because of some fabrication defect, but nevertheless, even this splitting is sufficient for demonstration of balanced heterodyne detection, and this is now as a function of wavelengths. We also can measure the far field profile of the laser to confirm that this is really operating in TM00 mode. Now this chips has just been shipped to our partner, GEM, for actual characterization of their performance in the heterodyne regime. And then we also have, we are working on the first mid-infrared photonic integrated circuits to produce narrow linewidth lasers. The concept is similar to what Javier has described already for near-infrared. The idea is to couple an active device to a passive section with a long effective passive length. This configuration is known to reduce the line width of the active device by simply increasing the length of the cavity so that the fluctuations due to spontaneous emission and carrier fluctuations in the laser and alpha factor of the laser are suppressed because the actual laser cavity is much larger than that of just the laser. The way we implement our narrow linewidth PIC is shown here. We have a ring resonator critically coupled to the bus waveguide that is then tapered to avoid any feedback, and then a strong dBi reflector to reflect the light coupled to this bus waveguide and couple it back to the laser. Our calculations following the formalism that is already introduced in this reference for the near-infrared lasers predict that we could, with reasonable losses in our waveguides, let's say half dB per centimeter, we could reduce the line width of a free running QCL from 1 megahertz down to maybe as low as 10-20 kilohertz. And these are some simulation results for the feedback spacing determined by the ring resonator radius and for the line widths as a function of coupling coefficient between the bus and the ring. Implementation is still ongoing. These are some of the PICs that we have fabricated recently. Fabrication was not exactly perfect. As you may see, there was some problem with the etching. But what you see here is the PIC itself. This is the laser. This is the bus waveguide to which the laser is coupled. This is the ring resonator, and this is the DBR section. So light goes from the laser into the passive, coupled to the ring, coupled to the drop waveguide, reflected off by the DBR section, and is coupled back to the laser. This is some zoom in on the passive waveguides. This is the coupling region between the passive waveguide and the ring. This is the connection from the laser to the passive waveguide, and this is the DBR mirror, which is fabricated here. It is all this basically AP is at the same height and etched roughly to the same depth, laser and the passive. So likely because of fabrication imperfections, the laser only worked in pulse mode at room temperature. And threshold current density is too high for the laser to operate continuous wave at room temperature. We need to lower it to the range 2 to 3 kiloamps per square centimeter. And this is likely due to basically high losses in the feedback loop. There could be some other explanations that we are working on it, that we are working to resolve, but basically the processing has to be improved to reduce the threshold current density of the device for it to be able to operate continuous wave. We see this several single mode emission of the laser, which correspond to a combination of a Fabry-Perot resonator modes of that external cavity and ring resonator modes. By adjusting the DBR coupling strengths and position, we could select only one of the two and operate device at just one single wavelength. Measurements of the line widths are subject to development of the CW laser at room temperature. Once this is done, we will be able to confirm our calculations that the line widths of this device is indeed reduced by 50 to 100 times. Far field profile is close to TM00. So in conclusion, I've described to you this nascent field of mid-infrared photonic integration. Showed you this DB QCLs can be monolithically integrated with passive waveguides. Waveguide losses are similar or even better than state-of-the-art silicon germanium platforms. High Q ring resonators can be demonstrated at 5 microns, but also at longer wavelengths. Monolithic integration and multiplexing of multiple intersubband active regions can be done. And within the INPHOMIR project, we demonstrate the first balanced heterodyne detector PIC for the mid-IR LiDARs. And more PICs are going to be developed for these other applications. Thank you for your attention, and I'll be happy to answer any questions.
Thank you very much. We're looking forward to receiving any question. Maybe it was, I've seen hands raised, but maybe it was an error. If you have any question, please write them in the chat and we will be pleased to ask to the speakers. At the moment, we have a question for Xavier. The question is, can you tell us some details about processing time of the structure you have presented in this session?
Yep. Yeah, processing time. The full process takes quite a significant amount of time. So I think we will need around 2 months to do a full process. So that's including all the waveguide etches and also the metallizations.
Okay. I hope that we have answered the question.
And then there's always the risk of equipment going down and things like that, but that's on top of that.
Okay, thank you. I have a question for Professor Belkin. In your opinion, what is the growth prospect of INP-based applications, and what are the major researchers in this sector?
I believe into the potential of mid-infrared photonic integration. In the mid-infrared spectral range, to be honest, the biggest market right now is the high-power mid-wave IR lasers. And in principle, mid-IR photonic integration can help in power scaling and also in beam forming. So, but also there are all these emerging applications such as, for example, chemical sensing based on photoacoustic spectroscopy. I think Sensorion, if I'm not mistaken, in Switzerland has just released some of the first CO2 sensor based on photoacoustic spectroscopy and QCLs, which is kind of the first mass market, maybe application for QCLs. There is an emerging field of free space communication with QCLs. There is strong research interest, at least in this area. And PICs are very well suited for, just like in near IR, for actually demonstrating high bandwidths and developing high bandwidths free space communication. Now, you asked about the major researchers. Okay, so okay, in Europe, this work is being pursued by Jerome Face Group in ETH. I think their main focus so far has been on frequency comp lasers, outcoupling light from some ring resonator-based frequency comp devices and reshaping frequency comp QCLs into pulses. They are FM frequency comps, so they need to be reshaped into pulses. So they applied photonic integration on Indium P for that applications. The group of Raffaele Calambelli in Paris is also working on developing mid-infrared photonic integrated circuits. Then there is, of course, then there is a group of I would not be able to say the name. It's an Asian professor at MIT who has demonstrated arrayed waveguide multiplexers at 4.6 microns, coupled to different QCL devices. This application is spectroscopy and power scaling. And then there is also a large body of work of people working on photonic integration on silicon. Some of the leading groups there are University of Montpellier, Terazi and Baranov are the PIs, where they grew QCLs and ICLs on silicon. And then there is a group of Delphine Marini in Paris that use this silicon germanium-based waveguides to demonstrate, for example, supercontinuum generation, and also they're working on some beam reshaping. So these are the names that come to mind. If you have any additional specific questions, I'll be happy to answer.
Thank you very much. I'm just interested to know from Professor Leitens your opinion related to the growth prospect of INP-based applications. Can you switch your microphone on, please?
In general or specific for this application, I think in general there's a lot of telecom and datacom applications of this type of integration, and of course once you have that in place, you can also use the same technology for sensing as we do in INPHOMIR. but because of the different requirements that you have, if you go to that sensing, then there might be different changes to the process might be needed, as I've shown in the presentation for the p-doping, for example. Whether monolithic indium phosphide is the answer to everything, that's a bit of an open question. I think once you can do things monolithically in a well-controlled and a very uniform way, it can be cheap. But the problem is, of course, you need a certain chip area. So all the functions that you do in indium phosphide, you have to pay for the indium phosphide, and which is certainly more expensive than silicon. So hybrid solutions might make sense. Yep, for depending on the application, hybrid solutions might make sense. Where yeah, there's all kinds of hybridization going on at the moment, and it's not so clear which process will finally yield the best devices. I hope that answers a little bit the question.
Yeah, sure. Thank you very much. So we don't have any other question at the moment. I just take some 1 minute to show you what INPHOMIR is organizing next, because our next event will be a training school. I don't know if you can see my screen. Okay, so in September we will organize a training school that is called From Platforms to Applications, the INPHOMIR School on Integrated Photonics for Sensing and Navigation. It will be held in Bari, Italy, and it is organized by Politecnico di Bari in collaboration with B-Warranty Next Innovation Hub, that is part of the project. We are defining the agenda, but you can see here just the topics that will be discussed. So we will start the first day on the 7th with an introduction about fundamentals of integrated photonics, and from photonic devices to systems and so on. And then the day after, we will talk about integrated photonics platforms, micro nano fabrication and integration, photonic sensor and applications. And the last day will be dedicated to EU policy dialogue. We will invite different EU-funded projects in the photonic sector to talk about their experience and their activity and results achieved inside the project. So please keep following us. Follow us on LinkedIn, and you will receive soon the information related to the opening of the registration. The event will be free of charge, but it will be in person. And I hope that some of you will be interested in participating, because it will be a very interesting and nice event that for sure will give you the opportunity to deepen the topics of integrated photonics. So that's all from my side. From our side, we have no additional question. So I just would like to thank you very much for being with us. You will receive in the next days a survey. So I kindly ask you to give us a feedback about how was this webinar, in order also to improve the other events that we are going to organize. Many thanks to the speakers, Lorenzo Mancini, our project coordinator, that helped me support us in the organization of this event, and also to Professor Leitens and Professor Belkin. And that's it. So thank you again, and have a nice day. Goodbye.
Thank you. Goodbye.
Thank you. Bye.
Thank you.